Welcome back. In this video, we're solving problem 5 from Chapter 2 of Computation and Measurement. The topic is Earth's orbit around the Sun, and we're going to use real astronomical data to answer two important questions. How many significant figures can we actually trust when we say the Earth orbits the Sun in a circle? And what errors do we introduce when we use the astronomical unit as a stand-in for the true Earth-Sun distance? Let's get into it. Here's the problem. Earth's orbit around the Sun is elliptical, not a perfect circle. But for many practical purposes, it's close enough to a circle that we approximate it as 1. The radius of that circle is the mean Earth-Sun distance, which is called the astronomical unit, or AU, and it equals 1.49598 times 10 to the 8 kilometers. That's 5 significant figures. The American Ephemeris, which is an official astronomical almanac, lists the actual Earth-Sun distance for every day of the year. It gives those distances to 5 significant digits as well. So we have two questions. Part A asks, given the real data, how many significant figures is it actually reasonable to use when we treat the orbit as circular? And Part B asks, what are the largest possible absolute and relative errors if we just use the AU instead of the real daily value? Here is the actual data from the American Ephemeris. These are the Earth-Sun distances on the first day of each month, given in units of 10 to the 8 kilometers. You can see that in January, the distance is 1.4710, meaning Earth is closest to the Sun. That's called perihelion. By July, it reaches 1.5208, which is the farthest point, called aphelion. Then it comes back down through autumn and winter. The AU, shown in the center, is 1.49598. This is the mean, right in the middle of the range. Notice that all values are between about 1.47 and 1.52. That spread is going to be the key to answering Part A. Now let's answer Part A. The question is, how many significant figures is it reasonable to use for the Earth-Sun distance if we're treating the orbit as a circle? The key idea is this. The error we make by assuming a circular orbit is at least as large as the spread between the largest and smallest real distances. The largest distance is 1.5208 times 10 to the 8 kilometers in July. The smallest is 1.4710 times 10 to the 8 kilometers in January. The range, or spread, is 1.5208 minus 1.4710, which equals 0.0498 times 10 to the 8 kilometers. Now look at where that spread sits in the number 1.49598. The variation of 0.0498 affects the second decimal place, the digit after the decimal point in 1.49. So the uncertainty kicks in at the second significant digit after the leading one. That means we can only trust 2 significant figures. In other words, saying the Earth-Sun distance is approximately 1.5 times 10 to the 8 kilometers, just 2 significant figures, is about as precise as the circular approximation allows. Now for Part B. We want to find the largest possible absolute and relative errors when we use the AU, 1.49598 times 10 to the 8 kilometers instead of one of the real table values. The worst case is when the real distance is as far from the AU as possible. Looking at the table, the farthest value from the AU is 1.5208 in July. So the absolute error is the absolute value of 1.49598 minus 1.52080, all times 10 to the 8 kilometers. That gives us 0.02482. Which we round to 0.0248 times 10 to the 8 kilometers. Now for the relative error, we divide the absolute error by the true value. That's 0.0248 divided by 1.49598, which equals approximately 0.0166, or about 1.7%. This matches exactly what the textbook gives us, 1.7%. So the AU is accurate to within about 1.7% of the actual Earth-Sun distance at its worst. Before we wrap up, let's quickly touch on dimensional analysis, because it's a technique that comes up throughout this chapter. The idea is simple. Units behave like algebraic variables. You can multiply, divide, and cancel them just like you would with letters in an equation. For example, if we want to convert 623 centimeters into meters, we multiply by the fraction 1 meter over 100 centimeters. The centimeters cancel, and we're left with 6.23 meters. The fraction we multiplied by equals exactly 1, so the value didn't change, only the units did. This is called a factor unit. The rule is, write your starting quantity with its units, then multiply by fractions equal to 1 that cancel the units you don't want, and introduce the units you do want. Keep repeating until you have only the units you need. This technique is used throughout science and engineering, and we'll see it again in the next problem. Let's bring it all together. The astronomical unit is 1.49598 times 10 to the 8 kilometers, 5 significant figures. But when we use the circular orbit approximation, we can only justify 2 significant figures of precision, because the real orbit varies by about 0.05 times 10 to the 8 kilometers across the year. Using the AU instead of the real daily distance introduces an absolute error of up to 0.0248 times 10 to the 8 kilometers, and a relative error of about 1.7%. The key takeaway is this: a circular orbit is a useful approximation, but the elliptical variation of Earth's orbit limits our precision to just 2 significant figures. Always match your precision to the accuracy of your model, not to the number of digits in your data. Thanks for watching, and I'll see you in the next problem.